Hi everyone, welcome back. In this video I'll be doing another projectile motion problem. If you want to be stronger than you were at the start, then pause the video at some point and try and make progress on your own. If you don't end up pausing, then watch the video again later and try again. With that said, let's get started. On level ground, a shell is fired with an initial velocity of 50 meters per second at 60 degrees above the horizontal and feels no appreciable air resistance. A. Find the horizontal and vertical components of the shell's initial velocity. B. How long does it take the shell to reach its highest point? C. Find its maximum height above the ground. D. How far from its firing point does the shell land? E. At its highest point, find the horizontal and vertical components of its acceleration and velocity. I'm going to start by drawing a picture of the shell. So here is level ground. Here is the shell. It's fired with an initial velocity, 50 meters, like that, at 60 degrees above the horizontal. So this angle here is 60 degrees. So this is the initial velocity vector. So the very first thing they want us to do is find the horizontal and vertical components of the shells. Okay, so before we do that, we have to choose a coordinate system. I'm going to choose the origin to be the shell's initial position. The y-axis is straight up like this, and the x-axis is horizontally like this. So to find the horizontal and vertical components, we have to draw the triangle of the magnitudes. So the hypotenuse is going to be v0. The component of the initial velocity along the y-axis is going to be v0y. And the component of the initial velocity along the x-axis is going to be v0x. So yes, it's very important to choose your coordinate system before you compute the components, because otherwise you need to have a coordinate system for the components to make sense, basically. So again, this is 60 degrees. So to express v0x in terms of the angle and the hypotenuse, I take the cosine of 60 degrees. This is the ratio of the adjacent side, which is v0x, over the hypotenuse, which is v0, and that is 50 meters per second. And if I solve this for v0x, by multiplying both sides by 50, I get 50 cosine 60 degrees. And 60 degrees is one of the standard angles for trig functions, and it just so happens that cosine of 60 degrees is 1/2. So v0x is 25 meters per second. This is one of our answers. This is the component, is the horizontal component of the shell's initial velocity. And now to express v0y in terms of the angle and the hypotenuse, I take the sine of 60. This is the ratio of the opposite side, v0y, over the hypotenuse, which is 50. Multiply both sides by 50 to solve for v0y to get 50 sine 60 degrees. Sine of 60 is square root 3 divided by 2. So this is 25 square root 3 meters per second, which is approximately, let's get out the calculator for this, 25 square root 3, 43.3 meters per second. This is the vertical component of the shell's initial velocity. All right, what's next? How long does it take the shell to reach its highest point? So we're looking for time, t. So the shell's motion is going to be a parabola because there's no air resistance. So it's going to look like this, very roughly. So for this part, or for part B, this will be our final position, and this will be our initial position. We're going to look at the motion in the vertical direction. So the kinematic equation is going to be y equals y naught plus, plus v0y times t, and then plus 1/2 ayt squared. So actually, this is the approach for part C. I'm jumping ahead of myself here. So for part B, we just need to know how long it takes, so t. So I'm going to use not the formula for position, but rather the one for velocity. So this is going to be v equals v naught plus at, but applied to the y direction. So this here is going to be our formula. At the very top of its motion, the vertical velocity, the velocity, the component of the velocity in the y direction is 0. It's at a complete standstill. It's not moving at all it's not moving at all up or down. So it's Vy is 0 at this point. V0y is 50 sine 60, what we calculated here. I'm just going to put 25 square root 3. Ay is the acceleration in the y direction. The only force acting on the shell is that due to gravity. So the acceleration is straight down. The acceleration is going to be negative g because I define my positive y to be up. Gravity points down, so that's why there's the negative sign. So minus gt. This t is the amount of time it takes for the shell to go from here to the top. So I'm going to solve this equation now. So I'm going to bring gt to the left. So gt equals 25 square root 3. And now divide both sides by g to solve for t. So let's get out the calculator now. All right, 25 square root 3 over 9.81. 4.41. That is in seconds because we are working in SI units. 4.41 seconds. So now that I know, okay, so this is the answer for part B. Now that I know the time, I can now find out what, find the maximum height above the ground. Okay. So now the maximum height, so I'm going to call the final y position here is going to be, I'm going to call it y max. So y max equals y0. That's the initial height is at 0. v0y, that's going to be 50 sine 60, which is 25 square root 3. Times t, and minus 1/2 gt squared. The t that we use here is what we calculated here, 4.41. So let's get out the calculator once more. All right, 25 square root 3 times the t, now minus 1/2, 9.81 times t squared. So we have a maximum height of 95.6 meters. This is our answer for part C. $95.6, yep. Okay. How far from its firing point does the shell land? So we're looking for the x value, the horizontal distance, and E at its highest point. Find the horizontal and vertical components of its acceleration and velocity. At its highest point, find the horizontal and vertical. So let's start with the velocity. At the highest point, as we said before, the vertical velocity Vy is going to be 0 because it's at a complete standstill at the top. It doesn't go, there's no vertical speed here. It's completely horizontal at the highest position. The horizontal, the velocity is purely horizontal, and it's v0x at this point here. The horizontal component of the velocity everywhere is v0x actually, because there's no acceleration in the x direction. Air resistance is neglected. Right, so those are the components of the velocity. Now the acceleration is at this point ax equals 0, and ay is negative g. It doesn't change. That's the way it is at every single point along the motion. All right, so let's move on to part D. How far from its firing point does the shell land? So in parts B and C and E, we took as our final position the top of the parabola, but now in part D, our final position is going to be where it lands, right here. So let's consider the horizontal. X equals x naught plus v0 xt plus 1/2 ax t squared. So t now. So now, because I chose this as my final position, t now represents the time to go from the start all the way to the to where it lands. So t is different from So this t right here is different from this t here. So x, that's going to be the final position. That's what we're trying to solve for. That's the final position. I'm just going to leave it as x. X naught is going to be the initial, is where my origin is. It's 0. Not 6, but 0. And now v0x, that's going to be 25. 25t, and now, as I said before, ax is 0 because the shell is not speeding up or slowing down horizontally. It's constant. It's constant. It's constant, yeah. So x equals 25t. Question now is, what is t? So I'm going to look at the so one way to do this is to consider the vertical motion now. So vertical, the corresponding equation is going to be y equals y naught plus v0 yt plus 1/2 ayt squared. So the final y and the initial y are the same. They're both 0. So 0 equals 0 plus v0y, that's going to be 50 sine 60, or 25 root 3, plus 25 square root 3 times t, and now minus 1/2 gt squared. So t is 0 at the very beginning, so t is going to be bigger than that. Our equation then is 0 equals 25 square root 3t minus 1/2 gt squared. So to solve for t, I'm going to divide both sides by t. 0 equals 25 square root 3 minus 1/2 gt. Bring the 25 root 3 to the left side to get negative 25 square root 3 equals negative 1/2 gt. Multiply both sides by negative 2. 50 square root 3 equals gt. And now to solve for t, I divide both sides by g. So t is 50 square root 3 over g. Let's get out the calculator. 50 square root 3 over 9.81. 8.83 seconds. So again, this is the amount of time it takes to go all the way from the initial position back down to the ground. And this is actually double of what this time is, and that makes sense because this is a parabola. The parabola has symmetry about the vertical axis, so it takes as much time to go from the initial position to the highest point as it does from the highest point back down to the ground. So it makes sense that t here is double of what it is before. Right, this is 25 square root 3 over g, whereas this here is 50 square root 3 over g. But that's not what we care about. The problem is asking for how far from its firing point does the shell land. So again, we want x. X is, where is it? 25t. So now that we know what t is, x is 25 of 25 times 50 times square root 3 over g. Calculator time. Let's see, 25 times. Copy and paste that. $221. Wait a second, not seconds. That is 221 meters. Right, because this is distance. Yes. So this is our final answer for part D. Yeah, I boxed the T, but we don't. It's not what the question's asking for. So just ignore this box here. Okay, so I believe that's it. Yeah. All right. So that's it for this problem. I'll see you in the next one. Bye, guys.